Hi, this is Andrew McLaren. I wanted to talk about colligative properties, specifically boiling point elevation and freezing point depression. And so basically, I'm going to go over the main idea with the formula, but I'm going to emphasize a lot with some models and help you understand what's going on about why, because I think that will help you be more successful and also able to do like a positive or a negative change when it's appropriate. Is the boiling point going up or down? Kind of hard to remember unless your teacher tells you, or you can reason through it. So I'm going to help you with a little bit of thinking through that. And then we're going to also think about what's going on with the energy and some graphs and look at some real world examples and some models to help understand what's going on with that. And then we'll do some actual typical problems. But the problems will be kind of near the end after we've thought through a lot. So you should be able to find the new freezing point and boiling point of a solution. But you also should be able to kind of explain the general ideas that give us this relationship. When we're talking about colligative properties, you're typically going to see this formula where you've got your change in temperature is equal to I times K times little m. And this is the formula that you might use for freezing point or boiling point. Depending on your class, your teacher might always tell you that like boiling point always goes up, freezing point always goes down, which is the case for salt, but it's not the case if you dissolve a gas in there. It actually has the opposite effect. We'll talk a little bit about that in a little bit, but I'm going to focus mostly on like the salt because that's what most people are going to be here thinking about and coming to this video looking for, right? Because most of the time when we're talking about a salt being put in a liquid, um, things can get a little bit confusing for people. There's a lot of words going on, but this math is very, very simple. So we got to kind of understand a little bit about why this formula has this relationship, and then the math is going to be easy. So we're going to work on building that understanding a little bit today. So basically, I is the number of particles. K is some constant that's dependent on the liquid that um, you're trying to change the boiling point of, and M is the concentration. So if you're putting in a lot of salt here, like it's going to make a very concentrated solution. That's going to cause a big change in T. If the salt actually dissolves a ton of particles, like it breaks up into like 4 pieces, that's also going to have a big effect on the temperature because it's causing more interactions with water. If you've got more charged particles in there, the water is able to interact with more things. And the constant, this depends on water. So you could have the same concentration and the same number of particles, but instead of water, maybe this is oil or some other sort of liquid. And then that's going to get slightly changed. The temperature change will be different for water than it is for like oil, even if you add the same amount of salt to it and you get the same concentration. So just be aware of that's kind of what's going on with this formula. And let's talk a little bit more about those variables, and then we'll get to modeling the stuff out and thinking about the main idea. So if we're talking about solutions, it's really important that we get these words down. So a solution has a solute and a solvent in it. And I've kind of color coded things here so you can see the solute is in purple. So like NaCl, table salt, that's an example of a solute. That's going to be some solid that's being dissolved. The solvent is going to be the liquid that you're dissolving into, like maybe water, H2O. And when we're looking at little m and big M, these are very similar. You can see it's got moles on the top and then kilograms on the bottom and liters on the bottom here for molarity versus molality. But what you see is that this is just the water and this is the solution. The volume of the solution changes with temperature. The weight of the water does not. So this is going to be like temperature independent. And that's because it's not a measurement of volume, it's just mass. That mass won't, the liquid's gonna expand when it gets warmer, but it's not gonna change its weight. Um, so that's kind of the reason that we use little m versus big M. Most of the time, little m ends up being close to big M. Like they're very, very close because in 1 liter there's a kilogram of water. That's the density of water. Salt water has a slightly different density. So again, it does throw things off with that density. Um, and it's very important to keep that in mind, right? Because the salts can affect how much volume the water is taking up as well, which is going to affect this M value as well. So if we really want this to be independent of temperature and the density of the salt, we need to use little m. So that's why we're using little m with this formula. Another way of remembering how all these words are related, it's totally silly and kind of dumb, but I always thought of like some musical instrument, like a lute, being stuck in like the air vents in my classroom. And that would help me remember that lute goes in the vent. If you're curious about where these words come from, though, it all comes from dissolved. Like solution means when you're solving something, you're loosening it up, you're getting something out of it, right? You're breaking up the parts. And so in this case, when you solve a salt, you literally break it up into its parts. Because it's dissolving when it's going into the water. It's breaking up and being spread out evenly throughout there. So we kind of talked about this a little bit. This is the number of particles. So if you're trying to dissolve like NaCl, that's going to break up into the Na plus and the Cl minus. So we've got two different ions that are made from this. But you can see like this is going to make one magnesium and two chlorines, right? Because these are each -1. This is +2. Sometimes we usually write this with a 2 here, but I just kind of want to show you. It's like, oh, this is 3 different things that are being made from here. So when you dissolve like 1 mole of MgCl2, you're getting 1 mole of Mg and then 2 moles of Cl for a total of 3 moles. So you've made 3 moles of ions now. That's going to have a significant impact, right? So if you're thinking about like NaCl and magnesium chloride, this one is going to have a bigger impact on temperature if everything else is constant, right? If we've got the same amount of stuff that we're adding to the same amount of water, this one's going to have a bigger I value. And so if everything else is constant, the change in temperature would be bigger. So you want to keep that in mind. That's kind of what's going on with this number of particles. And then K doesn't really matter what ions you're putting it in. It could even be something that doesn't ionize. So you could have like glucose, or like you could have something like this, like an organic chemical. That's not going to actually ionize. It's just going to be one. It's like it just stays as one block. And so that's not going to be contributing more ions that way. So it doesn't really matter what the ion is, it just matters the number of ions. And so because of that, this K value only depends on what you're dissolving it into. Like water is going to have a certain change in temperature. Oil will have a different change in temperature if you add the same things to them. Okay. Now to, in my mind, what actually explains what's going on here. So this is how I think of when we're dissolving, what's going on and why does this have this temperature change. So basically, I've got these little dotted lines to show intermolecular forces. We've got like a clump of some salt that then we place in some water and it dissolves. Before it's in the water, these things are interacting with each other, the positive and negative charges. They've got those intermolecular forces interacting and holding on to each other. But water, like this molecule with the 2 hydrogens and the oxygen, this is going to come and like kind of sneak in between these molecules and start interacting with that one, and it will get pulled off. Long story short, you have the oxygens, which have kind of like these negative charged ends, and the oxygen oxygen has the negative charge end, and the hydrogens are like kind of the positive charged end. Because water has that polarity, because it's got a difference in charge, it will end up interacting with these positive and negative charges in a salt. And they end up kind of pulling them out of the solid and dissolving them into the liquid. So you end up having something that looks kind of like this in the water, where the water's kind of enveloping or making these circles that go around the ions so that they're lined up, so that their positive charges are next to the negative charge, their negative charges are next to the positive charges, and they have this network of very strong interactions. So you can imagine here, if you're thinking about what's going on with the I and the K and the M and all that stuff, what we're saying is if you have more charged particles, that's going to have a big change in the temperature, right? So if you had something, it's kind of silly, but let's say like you could imagine something that its I was like something like 8 or 9 ions, then that's going to be making all these ions. And so that's a lot of ions for the water to interact with. And the water gets stabilized there. And those intermolecular forces make that water phase more and more stable, like a lot more stable. And so it's really interesting because now it's harder to get the water out of that phase. It's being held onto by these positive and negative charges. So if one of these wants to go off and evaporate, it's it's being held on a lot stronger by its neighbors and these charged particles. So it's harder to boil this off, aka it's got that higher boiling point, but it actually is also easier to melt it because the water wants to interact with these charged particles. It has more stability when it interacts with them. It's going to turn into a liquid because liquid water can rearrange and have the particles rearranged. Ice can't do that. The molecules are locked in place. So when we have a solid and you put salt on it, basically the liquid phase will start forming around that salt due to that stability that it now has. It's like, oh well, if there's charged particles up there, I've got enough energy now to be in that phase. Not enough energy to be in that phase normally, but now I do. So if you've got some salt, that's basically extending the liquid phase. You can think of it as like raising that boiling point and lowering the freezing point. So it's made that phase more stable. And then conversely, gases have the opposite effect. So if you have some water molecule and there's a bubble next to it, it's now can't interact with the other water molecules on the other side. And the scale is kind of weird because um, gases are like way further apart from each other than a liquid. And so the interactions, it's too far for these things to actually really interact, the distance between the liquid and the gas molecules in the bubble. So they don't really interact with the things in a gas. And therefore, when you have a gas and a liquid, you're making there be less interactions. Therefore, water suddenly becomes less stable. It will boil off easier, and it actually becomes harder to turn ice into that liquid phase. So it's really important to think about the salts and the gases as being opposites because it either is causing more interactions with the salts with the liquid phase, or it's causing less interactions with the salt or with the gases in the liquid phase. So that's one way to really think about that, and that's how I think about these what's going on with these ions and why that effect is positive or negative in those different situations. This graph really helps me understand visually what happens when you add a salt to some sort of liquid like water. Water normally has a boiling point of 100 degrees Celsius and a freezing point of 0 degrees Celsius. When we add water, it extends this liquid phase, like the liquid phase is literally longer on the graph, right? And it makes it so it's got a higher boiling point and a lower freezing point. And you can see what's kind of happened also with the other things. Also, it does affect the slope slightly. When you add in a salt, it takes more energy to cause some change, so it will cause the slope to change slightly as well. But the main point that I want to hit is that like we have a new boiling point and a new freezing point, and those are corresponding to what you would calculate using that formula. And you could imagine if you add more salt, it's going to make this go up higher and lower. Or if you've got salt that gives off more ions, it's also going to be higher or lower because there's more things to interact with, right? This is just a graph of the energy Q compared to temperature. And most people know, like, oh, higher temperatures is higher energy, but there's a common misconception around the boiling point and freezing point. As a solid is changing to a liquid, it stays at 0 degrees Celsius. It's a constant there. So there's a little plateau there. And same with a liquid turning to a gas. It's normally going to do so at 100 degrees Celsius. If we add salt to it, it might be higher though, like 101 or 102. If you add a gas, it has the opposite effect. You can see that it kind of like shrinks right here. The liquid phase gets much, much smaller. It's less stable. So it takes more energy to make a solid turn into a liquid. And it also doesn't take that much energy to turn a liquid into a gas because this is so unstable. Um, it might as well be a gas. Like if you've got not very many interactions holding the water in now because there's a gas preventing those interactions, you might as well turn into a gas yourself, right? You don't need much energy to be like convinced to leave there energetically. So that's kind of what's going on there. And then you can also think here, okay, it's much easier now to turn into a liquid because it's got all these interactions. That's stable. And so the liquid will melt, or the solid will melt into a liquid at a lower temperature, um, normally when we add in salts. I also kind of wanted to show this just another way of seeing this. Like you've got the energy of like the normal situation here, the gas, liquid, and solid, and you extend out that liquid phase when you add in the salt, and then you kind of shrink it when you add in the gas, right? That's another way of thinking about what's going on with these shrinking and extending the liquid phase and the stability of the liquid phase and what's going on with the relative amounts of energy. So here are a couple of real world examples to just help you build familiarity with this. So if you've ever been somewhere like in the Midwest where they have a lot of ice on the roads, there's a common thing, a practice of putting salt on the road, or they used to do that. They put other things on there like salts that will have a similar effect, but it's not like table salt, so it's not like corroding the bottom of your car. Uh, yeah, it was bad. I had one of my chemistry teachers telling me how she literally had a hole in the bottom of her car and you could see the road um, from where she grew up. In any case, when you have some ice on the road and you put salt on that, you can see that this is like the ice. Some water will form on the surface of that, and it's going to get pulled out of the ice phase and into this or that solid phase and turn into the liquid phase. Because now suddenly it's getting this additional stability from these ions and interactions with those ions, they'll turn into a liquid. And so this is something that people use to get ice off of the road so that people can drive on the road. But what's interesting is it actually gets colder. A lot of people think that this warms up the road. This does not warm up the road. And it actually, in many ways, is going to make it get colder. And this is the same reason that you use salt to make ice cream. So if you have the solid turning into a liquid, the energy and the state of the chemical, like it's spacing, you can kind of think about that as like gravity and like a satellite being further out, having more energy, right? It's like a higher energy system. It's got more potential energy in the chemicals and their positions. So it's at a higher energy state. So that required energy to turn that solid into a liquid. Where did that energy come from? Well, it came from the speed that the molecules were moving at. And so the molecules would get slower to break the interaction that they had in the previous phase and now be in the next phase. So, in other words, things will get colder. So, the matter itself, to get more space, it's going to need to cool itself down. So, the roads actually have gotten colder when you put that salt on there, but it's no longer got solid ice on it. Now, the same thing happens. There's a common like end of school year thing that I used to do with my students. Um, very, very messy. But basically, you have a Ziploc bag with milk and sugar and vanilla in there, and like I think that's it basically. And then a larger Ziploc bag that has ice cubes in it and uh, some salt, right? And so what ends up happening is these ice cubes they end up changing phase, right? So as you add the salt, the potential energy of that ice and turning it into a liquid is going to go up. It's going to a higher energy state. So it needs to get colder. So the whole thing gets colder. Like the liquid gets colder, and because it's in contact with the milk and the sugar in here, that will get that colder as well. This does not have any salt. So this has like a pretty normal freezing point of 0 degrees Celsius. So what you can do is you can start with ice that's at 0 degrees Celsius, and then you can put salt on it. It will turn into a liquid but get colder in doing so. And that will lower the system to being lower than 0 degrees Celsius, which will turn the milk and sugar the into the solid. So it's a really common misconception. I've had arguments with other chemistry teachers about this. Um, but adding the salt to the ice makes that ice get colder, which ends up affecting that temperature of the milk. Um, so yeah, it's a pretty common misconception, and people get a little bit confused about what's going on and why this thing's freezing, and it's a little weird, right? So don't worry if you're kind of like, okay, I'm not completely understanding this. You've got a foundation now, and now we can use that foundation for the problems. When we're looking at colligative properties, this is basically what you're gonna need in terms of information. Like you're gonna need to know the formula of the chemical, its concentration, and this K value. Unfortunately, a lot of teachers will give you things where you need to do like a little stoichiometry before and after, like in this problem. So we'll talk a little bit about that. It's kind of nasty because now you're having to use some of these old skills that you might have forgotten. But um, I'll try and help you out with some of that stoic as well in this video. I do have a whole video on conversions and dimensional analysis as well, so you should check that out if you struggle with that part. And then there's sometimes they'll make you go backwards where they're like, okay, now tell me the molarity. I'm telling you what the new temperature is. You should be able to use other information to tell me what's going on with that. Interestingly enough, they didn't tell us what the salt is here, but does that matter? No, because no matter what that salt is, it's as long as it's got the I value, then we should be able to do that. Yeah, I was just thinking about it. Yeah, they would let's say that the I value was given here because we would kind of need to know that it's something how many particles are being made. So it's not breaking apart, it's just staying as one thing, right? One particle in the solution. Okay, so this first one, if we have this chemical, I can see that the like let's go ahead and change that so that's black. Okay. So like beryllium F2, if you think about that ionizing, it's gotta be something like this. And again, I'm gonna just do it a little bit from the atypical format. Normally we'd do like 2F, but I just want to show that there's three things here. So this is normally shown as like something like that. There's 1, 2, 3. So the I value is equal to 3. So that's important because now we know that this chemical is going to break up into 3 pieces. We also know the concentration here, and they've given us little m, and we know the K value. So if we're looking at change in T, it's equal to I, K, and then M. We have I, we have K, and we have M, so we should be able to find that change in T, excuse me. Okay, so we've got 3, and it's kind of weird the units on these guys, but then we've got 0.51 degrees Celsius, molar or molality, and then this is going to be the concentration in that molality, the 0.75. And then what we can do is we can just do a little canceling of the units. Part of me wants to put particles down here because there's 3 particles and it's kind of canceling out, but they don't typically write that in terms of the units, so I'm not going to do that. So we get 3 times 0.51 times 0.51, and then times that by 0.75. And it's always a good idea to just double check if something's reasonable. Like with these numbers, this is like 3 times a half, so that's like 1.5 times 3/4. Yeah, so it's going to be a little bit less than 1.5. Yeah, that sounds reasonable to me. So this is 1.14. And if we want to do sig figs, that's an absolute number, so we don't include that because you can't really do decimal points on this. It just wouldn't make sense. These are whole numbers and they have to be whole numbers, so you don't include that in sig figs. So I think they gave us 2 sig figs, so we can only do 1.1. This is degrees Celsius, and that's going to be our change in T. Okay, and then if we look at our new temperature, we're going to have like it was 100 degrees Celsius plus 1.1 degrees Celsius. So now we've got a temperature of the boiling point is going to be equal to 101.1 degrees Celsius. And then sig figs, if you're doing that here where you're doing the addition, I mean, we could say that this was accurate to that place value. Let's say that we knew that that was accurate to that place value, so we can keep that as is. Okay, I think that that's everything that you need to do for that first part. That's the general idea. Is like, okay, I know what my particles are. I know what my constant is for this phase change. Water does have different K values for its boiling and freezing points. So just keep that in mind. It kind of makes sense. In other words, we're basically saying like the slope here is a little bit different for like the boiling and the freezing point, how much energy you need to put in to get a change in temperature. It's gonna be a little bit different, which is it kind of makes sense. It's a different process. Same substance, but different process going from the different phase changes. Okay, so this has got a little bit of prerequisite skills where you're gonna need to know what these chemicals are. They've given us grams. So they haven't given us directly the I, K, and M. So it's kind of hard to find that change in temperature now. Oh, also I knew it was gonna be 100 degrees Celsius. That's what water normally boils at. So I added that to that, what water normally boils at. That's why we've got that 101 degrees right there. So if it's freezing, you gotta be at 0 degrees Celsius and then compare from there. So they haven't directly given me much information, but I do have like the KF right here for water and the KB for water. I think I also got from the last problem. Yeah, yeah, it was this guy right here. So we can just copy paste that down. Just gonna get rid of you. And so we're gonna need to do the change in temperature for the boiling and the freezing point because remember, we've got a new boiling point and a new freezing point when we've added this in. So they've given us Ks. They have not really given us Ms, but we can take this grams information to figure out the molality. So we're gonna need to use some like it's molar mass, and that will get us to moles, and then we can plug in the moles into here. Yeah, and then this is gonna be grams of water. I think we just need to turn that into kilograms. Yeah, because they gave us grams, but we needed kilograms. Because if you remember the little m, the units of that is normally kilograms. So if we're talking about that little m right here, or yeah, the little m, usually in kilograms right there. So we were in grams, we need to go to kilograms. So there's a little conversion here, a little conversion there, and then I think we can get from the name, we can figure out the formula, and that should give us the I value. So sodium chloride, that's NaCl. So that just breaks down into Na plus and Cl minus. So the I value is 2. It makes 2 particles. So yeah, we have our I value. That's good. Now what we need to do is we've got our 45 grams of NaCl, and we need to do a basic conversion. I'm going from grams to moles. I always write in my units first. And then I've forgotten this off the top of my head. I'll have to look that one up. But then we should be able to do the conversion pretty easily. Okay, so the molar mass for NaCl is 58.44. I also have a whole video on how to find molar masses, so check that out if you're struggling there. And this is for the NaCl. And yep, it's grams of NaCl. And so we should be able to get the moles there. And so if we get, what's that, 45 divided by 58.44. This is why it's good to do this with the video, right? Because you can go back and rewatch parts and skip the other parts that you don't need. So let's do 0, 0, 2. So that's our moles. They didn't really ask for moles, so we'll get our change in temperature and then plug that in as needed. So we've got moles, which is good. We've also got grams of H2O. This is why I write in the substance, right? Because I want to make sure I've got the right grams I'm plugging in into things. I've got grams of H2O and then kilograms. Yeah, you probably could do this in your head if you're one of the kids that likes to do that, which I know I kind of like to do that, but then it throws me off, right? I very much do the wrong thing sometimes. But yeah, this should be 0.500 grams H2 or kilograms. Okay, so now we can take those 2 bits of information because we've got moles and kilograms, and we should be able to use that to write our little m. Little m was equal to moles over kilograms. And so we can see it's going to be the 0.77002 of what we've dissolved. And then that's going to be over 5. All right, let's see what we get when we do that conversion or that calculation. Sorry, 0.5. Okay, so we get 1.54. And I think that was um, our molality, so that's the little m. Is it 0, 0, 4? Move you over. Um, they didn't ask for little m. They're asking for the change in temperature, so we'll just leave that with its additional numbers. Okay, so now we do have m. So we've got I, k, and m, so we should be able to do our change in t. The change in t was equal to, it looks like I of 2. And then we've got a k value of, and you can kind of see I've set up my formula there. I could rewrite it down here, but just because I can see it, I'm going to keep it. I'm going to use, yeah, sorry, the formula up here as a reference for working down here. This thing doesn't track when I move it around like this. Only my mouse does, so that's why I sometimes do that. I almost pulled out my computer. So if I'm trying to do, let's say this is for the boiling, because we got to do this for the boiling and freezing. I'm just gonna remind myself of that. So I've got 2, and then the KB for water. We gotta make sure we're using the right KB, right? So this is for boiling. This is for boiling. And then 0.5. Okay, so that would be giving us our change in temperature there. So we've got, and ask yourself what would be a reasonable number from this, right? It's gonna be basically that. And we get 1.5708 degrees Celsius. We could then round to, what is this going to be? Get rounded to 2. Okay. 1.6 degrees Celsius. So the temperature of the boiling point is now going to be what was 100 degrees Celsius plus this new correction factor. And so now water is going to be boiling at 101.6 degrees Celsius. And, oh no, I messed that up. Okay, so we've got our new boiling point. The freezing one is going to be very similar, but we got to be a little bit careful because now it's not boiling, it's freezing, and it's going to have a slightly different K value because it's a different process. Same substance, but different process. So this salt's going to interfere with the ability for it to freeze or melt slightly differently because it's a different process. And then this is the 1.86. And it looks like, yeah, it's a lot harder to get the the freezing point to change than it is to get the boiling. Or actually, no, much harder to get the boiling point to change than the freezing point. Yeah, because this will cause a bigger change in C for some change in M. Okay, long story short, what is this? 2 times 1.86 times 1.54. Okay, we got 5.7288 degrees Celsius. We can say that that's going to be, we simplify that, it looks like it's going to get simplified to 3 sig figs. 5.73 degrees Celsius. That's the change in freezing point. So the new temperature is going to be relative to 0 degrees Celsius because we're talking about water. And you usually are talking about water with this, water and salt. Okay, and so the freezing point should go down. Because as we've talked about this is where like conceptually understanding really helps. If we're talking about a salt, it extends this liquid phase. It's getting all these interactions. So the freezing point should be lower and the boiling point should be higher. When we're talking about salts, that is. Remember, gases are opposite of that. Okay, so the new freezing point is going to be at negative 5.73 degrees Celsius. Okay, last one. So if we're talking about the molality of a solution, we know that new boiling point is 102.805 degrees Celsius. What we can say from that is that the change in temperature of the boiling point was 2.805 because it was 100, right? So 102, 8.05 minus 100 is just 2.805, right? So we've got that as our change in temperature, which if we remember our formula, which always good to try and memorize your formulas. It's just one less thing to look up while you're juggling all the information of the problem, right? So if you can overlearn that, that helps a lot. So we have I, we have this thing, and we have the KB of water. So we should be able to find molality. We can rearrange for this, so we can say little m is equal to change in TB all over I times KB. If you divide both sides by I times KB, that should be what you get. And we have all of that information. So yeah, we should be able to just plug and play with this. The I for this was 1. You do need to know that. You know, this could be a number of different chemicals, but they're just breaking up, or when they are put in salt, they just stay as like a single unit from the chemicals formula. So we've got 1 particle there, and that's going to be times the KB, which I think was the 0.51 degrees Celsius, right? Just double check that. Yep, that's the KB. Okay. So if we plug that in, what do we get? 2.85, and then divide that by 0.51, 5.5. And that sounds reasonable to me, given that I'm dividing by like a half. So, yep, 5.5 degrees, or sorry, not degrees. This would be the molality. So that'd be the moles per kilogram of whatever this mystery substance is. We'll just go with a question mark because, you know, we don't know exactly what the chemical is, but I always write the chemical next to molality, so I feel like I should write that in there, right? I don't know. All right, well that's the typical problems. Be careful. You got to make sure that you're going in the right direction, and if you're not sure what that direction is, I would watch a little bit about where I was talking here about the clump of the solid. I think that'll help people to rewatch some of that after we've done some of the math. So yeah, thank you for joining me. Thank you for McLearning with me. I've got a few more offers that I'd like to let you know about, and remember, like and subscribe. For each video on YouTube, I am making an interactive version using HP5. These will be for sale on Podia, and if you click on the link in the video, you should be able to go directly to that product. I also have 2 demos I'm going to be linking so you can kind of see what these products look like. So I would recommend checking out those demos. I also offer one-on-one remote tutoring through Wyzant. Please use the links that I have linked below. That way I can get 100% of the hourly rate as opposed to 75. Each video also has a link for my Patreon, and you can join at the $3 level to get some resources I use for tutoring or to support the channel. And I also have a $5 raffle level, which you could either get some free online tutoring or 5 interactive lessons for free. You choose which ones. And then I also have my Teachers Pay Teachers, which has some old lessons that I made from when I used to be a teacher. I may be adding to that. Thank you for spending your time with me. I hope that you learned something.